Hi, this video is going to take you through the quantum mechanical model of the atom, how that has improved upon the Bohr model of the atom, and how that leads us into understanding and applying electron configuration. So just a quick recap from the last lesson. We learned about the Bohr model of the atom. Some things were great about it. First off, looking at the fundamental idea of quantization, the fact that electrons exist in definite, discrete energy levels. The other thing it does is it incorporates the idea that electrons can move from one energy level to another by absorbing or releasing energy. And it explains the emission spectra of hydrogen. So all of these things were fantastic about it. So just a quick recap. Here was your example when we were looking at the hydrogen spectrum of the emission spectrum of hydrogen, and you notice that specific releases of energy resulted in 4 visible lines. Problems with the Bohr model of the atom is that the position of the electrons are actually not fixed. The energy levels are actually not circular or spherical in nature, as that picture suggests back there. The scale and the size of the atom is not as the diagram predicts. Calculations, although they're correct for hydrogen, they don't explain any other atom that has more than one electron. So not very useful in that respect. And the electrons are not subatomic particles, essentially orbiting the nucleus. So from that model, various discoveries arose over the next 15 years or so that led to the quantum mechanical model of the atom. So a big aspect is the concept of probability. So that came from Erwin Schrödinger. If you've ever Googled Schrödinger's cat, there's lots of great memes on that. So the idea that applying probability and the ideas of quantization to waves. And so essentially that results in an equation that predicts the probability of finding an electron with a particular amount of energy at a particular location in the atom. So what does that mean? So essentially they came up with maps of regions in the atom that have a particular probability for finding the electron. And they called these regions orbitals. And so those orbitals are where we have a very high probability around like 90 to 95% chance that the electrons will be found in that area when it has a particular amount of energy at any given time. So it's a lot less specific than these kind of circles orbiting the atom. So an example, if you think of baseball, for those of you that understand baseball, pretty simple. If you have a pitcher throwing the ball to a catcher and that ball follows a path, that would be how we would describe an orbit. But if you think of it from the batter's perspective, that batter has to swing their bat in literally a split second and try and figure out the highest probability where that ball will be coming. So you'll notice that they're going to try and swing the bat in that high probability region. They have no idea if the ball is going to be there. There's a whole bunch of different locations that the ball could be, but it has the highest probability in the strike zone, and so they're going to swing their bat in that strike zone because they have the highest probability of getting it. So that whole strike zone essentially would be the orbital. Okay, so the probability is very high that the ball will end up in that area. So in Schrödinger's wave equation, there are essentially 3 integers, and they're called quantum numbers. Essentially, they quantize energy. We're only going to focus on the details of the first quantum number. We're going to explain all the aspects of the other 2, but you're not going to be responsible for memorizing and applying quantum numbers other than what's called the principal quantum number. Essentially, that value, the symbol of n, specifies the main energy level for the orbital. Okay, so the first energy level, second energy level, third energy level, n equals 1, n equals 2, n equals 3. So in that respect, it looks similar to the Bohr model, but it gets a little bit more complex. Okay, so essentially, excuse me, essentially, each principal energy level or energy shell has one or more subshells. And the number of subshells is actually equal to the principal quantum number. So for example, in n equals 1, there's one subshell. In n equals 2, that second energy level actually splits into 2 subshells. And the third energy level splits into 3 subshells. Fourth into 4 subshells, etc. Those subshells are given a letter. Sorry, that's my child's toy going off randomly, if you can hear that. So they're given a letter, either S, P, D, or F, and that's based on basically mathematical. They have names. I can never remember what they are. All you need to worry about is the letters S, P, D, and F. And each kind of sublevel, so the S sublevel or P sublevel or D sublevel or F sublevel, has orbitals within that with a particular shape. And that shape represents a probability map where 90% chance that you're going to find electrons in that region. So S orbitals look a certain way, P orbitals look a certain way, D orbitals, and then F orbitals look a certain way. So essentially how that's organized is here. This is a good representation. So in the first energy level, there's one subshell, and that subshell is called the S subshell, and there's a specific type of orbital in the S subshell. In the second energy level, there are two subshells, and then there's the S subshell and the P subshell. So we call it 2S and 2P. And there's specific orbitals within the S subshell and within the P subshell. All the orbitals within a subshell are identical in their shape. They just may differ in their orientation. In the third energy level, there are 3 subshells. So there's a 3s subshell, 3p subshell, and 3d subshell. And all s subshells will be the same shape. What's different is going to be their size. So all the s's would be the same shape, but different size. And then all the P's would be the same shape, but different size, etc. Okay? And then when you get to the fourth energy level or shell, there's 4 subshells. That's when you get S, P, D, and F. So you have 4S, 4P, 4D, and 4F. So a good analogy is thinking about an address, where you're getting more and more specific. So the shell would say, for example, be the city, so Toronto. The subshell might be the street that you live on. Okay, the specific subshells might be the house or the building, and then the orbitals within that would be the apartment within that building, let's say. So how does the 1S subshell differ from the 2S subshell? If you're paying attention, you'd know the answer. Here's just an example of a probability map, just a little better representation than these right here, showing that it's actually not like a ball, it's more like a cloud, right? So there's just a greater chance as you get towards the center, higher probability. As you get towards the edge, a smaller probability that the electrons will be found there at any given time in that energy. Okay, so the p orbitals, sorry, I'll backtrack a sec. There's one type of orbital in the s subshell, and there's one s orbital. So in the 1s subshell, there'd be one s orbital. In the 2s subshell, there would be, again, one orbital. That's the s orbital. When you get to the p subshells, there are actually 3 p orbitals. They're all the same shape in different orientations. So you notice how if you think of them in 3 dimensions, the px would be along the x-axis, the py along the y-axis, pz along the z-axis. And then the d orbitals, 4 of them are the same shape, but different orientations, and the 5th one's a little bit different. But essentially, there are 5 of them. So every d sublevel or subshell has 5 d orbitals. Thankfully, you don't need to memorize and remember the shape of the d orbitals. You just need to know how many there are. Whereas for the p and the s, let's go to that one. For the p and the s, you do need to know the shape as well as how many there are. Okay. And then f, if there's one s, 3p, 5d, guess what? You're right, there are 7 F subshells. So key things for these subshells is the subshells within a principal shell have slightly different energies. And so, for example, S would have the lowest energy, P is a little bit higher, D is a little bit higher, and F is a little bit higher within that shell. And then this just summarizes how many orbitals are in each of those subshells. Seems a little complicated, but it'll make a lot more sense, and there's some diagrams that I'll show you further on. So as in the Bohr model, atoms will gain or lose electrons as the electron leaps between orbitals in different energy levels or shells and subshells. So quite often I say level and shell. They essentially can be used interchangeably. So level and shell mean the same thing, and sublevel and subshell mean the same thing. It doesn't matter what you use. Okay, same idea. But the difference is they're going to be jumping between not just the levels, but also the sublevels. And that's one of the reasons why when you get to multi-electron atoms, you see a lot more lines, because there are a lot more combinations of essentially transitions. And just like before, the ground state of the electron is in the lowest energy orbital it can possibly occupy. And if it absorbs energy, it'll move to a higher energy orbital, which is the excited state. So the same principles apply as in the Bohr model. So both of them predict the spectrum of hydrogen very accurately, but the Bohr model doesn't predict the spectra of multi-electron atoms, whereas the quantum mechanical model does. So therefore, it's a more robust and more accurate representation. So I'm just a quick reminder, we're going to be using the periodic table for the second part of this. So it would be helpful if you had the IB periodic table printed out, a copy you can kind of play around with so you're not flipping back and forth on the screen. And essentially the second half of this unit is all about the periodic table. So I would definitely recommend having just the periodic table from the data booklet printed out so you can write on it, color it, make some annotations.